Recording. All right, Aki, A-K-I-H, is not here. My last name, Blount, B-L-O-U-N-T, not here. Boggs is here. Connor is here. Clay, last name Clay, not here. Last name Clayton, not here. Ellis is here. In WVSU here. I don't think Paul is here yet. No, not yet. Green is here. Harrison's here. Hinson's here. Last name James is here. Kesterson's here. King is here. Lewis, not here yet. Then the cube's online. Morrison's here. First name Grace, like actual first name, not nickname. There you are. Is here. Are you wearing WVSU gear by any chance? Okay. Rice is not here. Ward is here. Wilcox is here. Wilder is here. Parks, not here yet. That's 8. I called the list. Did I miss anybody? All right, hopefully some people come in before we actually start the lecture. I'm just gonna repeat some information I've repeated before. I've already made a video showing you how to do this. I just haven't shared it yet because I'm trying to make a better one. But today is lab day, right? So we're gonna meet here at 10 o'clock in this room. Don't be late, right? So you can't be late to lab, unlike lecture. You have to be on time. I mean, you should be on time to lecture too, but you just can't come in to lab if you're late, and then you get an F. All right, Paula is here. Anyway, so I'm going to very quickly show you one more time how to do a lab, how to get it very quickly. And again, I'd like to make a better video later. This is recording, so this is going to be one of the videos. Anyway, when you go to WVSU Online, there's a few ways to find your lab for the week. But I'm just going to show you the most easy, straightforward way. And again, there are other ways. Just go to WVSU Online, scroll down. It's all chronological, right? So there's the intro stuff, course announcements, syllabi, bunch of procedures. Then there we go, module 1, that's what we are, right? Weeks 1 and 2, we're in the second week, so we're in module 1. Scroll down, and then here we go. There is the lab. So you click on that. Now, a lot of you have already done this. A few of you haven't yet, because you did the pre-lab, you just didn't do it the right way. So I'm going to show you the right way and to make things easier moving forward. So here's the lab online. You need to open up the worksheet, so you just click that link and it pops up. This is the master copy. You don't have access to the copy. Don't go up there and where it says, request access. You don't have access. This is the master copy. So go over here, file, make yourself a copy. You're definitely going to want to copy the comments and suggestions. Make a copy. There we go. And then once you've done that, that's your document. That's the document you're going to use for the pre-lab and the lab. So for this week, that whole document, that's it. Does it make sense? That's it. The whole thing is the same document. Then you do the pre-lab, and once you're done with the pre-lab, you go up here to the share button that I don't see. See, and I knew something would go wrong. But anyway, usually up here there's a share button, and you would click that and you would share it with me, but it's not showing up for some reason. Lucky me. And then once you've shared it with me, that's how you turn in the pre-lab, right? And then once we meet today, and then we actually do the lab, and you fill out the rest of this stuff, like, past the pre-lab, and you fill out the actual lab. All these questions here, you're going to fill that out, right? Anyway, pretty straightforward. You fill all that out, and then once you're done, I know you shared it with me, but that's how you turn in the pre-lab, right? So once you're done, you go to File, Download. You're going to download it as a PDF. All right, there we go. I'm downloading it as a PDF. And then, again, I suggest doing this Wednesday before you leave lab, but technically the due date is Friday. Come in here up here, and again, you're in lab 1. Yours is going to look different than mine. I'm the teacher, so I don't have a button that says submit. Somewhere down here is a submit button. So you're going to hit the submit button, upload your file, and that's it. Does that make sense? All right. There's no pressure. The only pressure you should be under is a time constraint. So make sure you get it turned in on time. And what I mean by no pressure is don't worry about screwing it up. If you do something wrong or turn in a horrible lab and miss a bunch of points, it doesn't matter. I'll return it to you and say, this is what you missed, and then you can fix it. right? This isn't like a test. It's not like you turned it in and that's your grade, we're done with it. Yes, ma'am?
This is the same document from last week, right?
Correct. To make sure you guys understand, she's asking it's the same document as last week. Yeah, so the document that was due last week, last Friday, the pre-lab, it's the same document. So you filled that document out, you shared it with me on via Google, and then after today, after you fill it out, then you'll upload it to WVSU Online. Also, again, since me and the TA will be here in lab, before you leave, you should really come, bring your computers, and I'll show you how to upload your document. Even if you're not done with it, just so you can have practice, like, all right, I'm not done, I'm not ready to turn it in, don't worry about it. If you don't mind, come to us, let's go ahead and upload that document so you get practice doing it. And then maybe you can even leave a little note that says, this is not my final draft, I'm gonna upload the final draft later. That makes sense? Let us help you. And then after this, I think it'll be smooth sailing. It's always hard the first lab, because you're trying to figure out how things work. All right, any questions about lab? All right. Really quickly, we had some people come in, so let me just do this very quickly. Aki is here. Blount, B-L-O-U-N-T. Clay, Clayton, Lewis, right? And that was it. I think that's how many people came in. Anybody else that I didn't call? Nice and easy. All right. Check, make sure I'm still recording. I am. All right, here we go. Let's jump back into the chemistry chapter. So the first word for attendance is radioactive. I think that was the last word for attendance on Wednesday, but I don't remember. Anyway, radioactive is the first word for attendance. If you're online, LendaQ, or if you're watching the video, instead of just sending me the words, pay attention now, send me a screenshot of me pointing at the word. And I'll read this, not you guys, but if you're online, instead of just sending the words, I want a screenshot of me pointing at the word, please. And we'll do that for all the words today. All right. And if you missed it, I guess you could watch the video later and do the same thing. But that's how it's going to go today. Anyway, any questions about that? Okay, radioactive isotopes. This is not in your textbook, so I'm not even going to talk that much about it because I'm definitely not going to test you on it. But I don't know if you've ever heard of carbon dating. We can use that to figure out how old some things are. Because right now, if you were to take like a survey of all the carbon in the atmosphere, there's a certain ratio of how much carbon-14 there is versus how much regular carbon there is, which is carbon-12, right? I don't even know it. Let's just say it's, I don't know, 75% normal and 25% carbon-14. We know that's the normal ratio. But as carbon-14 gets old, it starts losing neutrons. And that's the point you do need to know, not necessarily about carbon. But remember, if you change the number of neutrons, you have an isotope, which is what you need to know for the exam. Anyway, as it starts losing neutrons, it becomes carbon-13, and then finally it becomes carbon-12 again. And it does this in a predictable manner. So we know, if we can see how the ratio of how much carbon-12 there is versus carbon-14, we can tell how old something is. But again, it actually gets a lot more complicated about it than that. You can read into it if you want for independent work, but I'm not going to test you on it. So any questions about radioactive isotopes? All right. And again, that's from your old textbook. So I had it in my PowerPoints, and I thought I might as well include it just in case you guys are interested in that. All right, chemical bonds. Actually, a really quick reminder to tell you what we've talked about so far. On Monday, we talked about atoms and what they're made up of, which is protons, neutrons, and electrons. We know that the nucleus has protons and neutrons in there. We know that the electrons are on the outside. We know protons are positive, neutrons are neutral, electrons are negative. We know protons and neutrons have a mass of 1. Electrons, as far as we're concerned, don't have a mass. That's what we talked about. Now we're going to kind of get into finally chemical bonds, right? Actual chemistry. As far as we're concerned, and I mentioned this on Monday because someone asked a great question, but as far as we're concerned, it's only the electrons that are directly involved in chemical reactions. So as far as we are concerned in this class, it's all about the electrons. Not that I'm going to test you on that, but when I do give you questions about chemical reactions, you should be thinking to yourself, all right, I didn't know about these electrons. So let's get specific. How does this work? It's the number of electrons that determines the chemical property of any given atom. And again, that's not going to be a test question. That's something you need to know to be able to figure out the test question that I'm going to give you. Definitely, you'll need to know it to figure out some stuff for lab next week. All right, and I'm gonna show you a picture of this later. Actually, I'll try to do it now. Remember on Monday I said there's different ways to draw atoms. I said the way that we're gonna draw them in lab and a lot in this class is it's called the planetary model, where we draw rings and stuff. Actually, we can do that one. I can't. Anyway, so if we're looking at an atom, the inner ring holds 2 electrons, right? So if this is any old random atom, there we go. We've got 2 electrons on that inner ring. All of the other rings hold 8 electrons. So, and there we go. This second ring has 1, 2, 3, 4, 5, 6, 7, 8, right? As far as we're concerned, and this isn't true, this will work for our class, for our purposes, but as far as we're concerned, for every ring after that, every ring holds 8 electrons. Because that's going to work for the problem solving that we're going to need to do in this lab and in this class. If you're interested for independent work, you can look it up and actually tell me what the actual situation is. It's not true that every other one starts holding 8. The first one definitely holds 2. The second one definitely holds 8. And if you're interested for independent work, look up the rest, where the rest actually hold. But again, as far as we're concerned in this class, that's going to help us figure out the problems that you're going to be facing. All right, here's the other very important part is this bullet point right here. A full ring, outermost ring, means it's stable, which means it's not reactive. If it has a full ring, outermost ring, then it doesn't need electrons. It doesn't need to give away any electrons. It's happy, so to speak. So because of that, it's not going to be interacting with other atoms, therefore it's non-reactive. Does that make sense? You definitely need to know that. And again, that's not going to be a test question where it says, what, a full ring equals a stable atoms equals what, right? It's not going to be that. But you will have a problem-solving question, and to solve it, you need to know that if it has a full ring, it's stable. So again, if it has a full ring, it's not reactive. On the flip side, that's what chemical reactions are all about, is trying to get that full ring. Reactions enable the atoms to transfer or share electrons. So that's what they're trying to do. That's basically what a chemical reaction is. Again, it's all about the electrons, right? So basically, as far as we're concerned in this class, chemical reaction is all about trying to get a full outer ring. Whether you're giving electrons away, or taking electrons, or sharing electrons, that's what it's about, is trying to fill that outer ring. And because of that, because they're either sharing electrons or giving them away or taking them, atoms stay together because of these chemical reactions. And that's what we call a chemical bond. A chemical bond is when 2 or more atoms are interacting with each other because they're trying to get a full outer ring. And all of this is called the octet rule. I'm not going to test you on what the octet rule is, but just so you know, when you're reading it in the textbook, that's what it is, right? So I put an X there, again, just indicating that I'm not going to test you. I'm not going to ask you what the octet rule is, but you do need to know all this information to do some problem solving. So any questions about this slide? Okay, next slide. Cells are constantly rearranging molecules. This is not from your textbook, by the way. This is important information. It's from the old textbook, so I left it. And what I mean by they're constantly rearranging molecules is they're breaking bonds and forming new ones constantly. That's actually what keeps you alive. You need energy to be alive, right? And that's where the energy is coming from. Ultimately, it came from the sun, but through a bunch of other reactions in the environment, eventually it got into you. But yeah, that's what keeps you alive. So this is literally a matter of life and death, even though you don't think about it. You probably don't think of yourself as a bunch of chemical reactions happening, but that's exactly what's happening. Anyway, changes in chemical composition of matter are what we call chemical reactions. And again, I'm going to put it next to this. There will be questions about chemical reactions, some problem-solving questions, but I'm not going to ask you the definition of a chemical reaction, but there you go, that's what it is. According to the old textbook, that is the definition of a chemical reaction. Changes in chemical composition of matter. And I think your new textbook will have the same or similar chemical definition. And once again, I'll remind you, these are all great independent work topics. So again, I'm telling you, this is the definition of chemical reactions according to your textbook. For an independent work topic, you can look it up. It's like, all right, well, I believe that, you said that this was the definition of a chemical reaction. According to this source, this is the definition of a chemical reaction, right? I love it when you question me, question the textbook. Anyway, chemical reactions include two things, a reactant and a product. I love this because it's one of the few things in science where they don't give it a weird name. The name actually makes sense. Right? The reactants are the starting materials. Those are the things going into doing the chemical reactions. And the products are the end materials, right? It all makes sense. That makes sense in my opinion, right? The reactants are the starting material, the products are what we're into. In this class, this isn't all chemistry, but in this class, you see this chemical equation on the bottom. We have something on the left, and we have an arrow pointing to the right, and we have something on the right. Now in this class, it will always be like this. The chemical reactions will always be reactants on the right, products on the left. The arrow will always be pointing from reactants to the products. Does that make sense? You should definitely know that. Not that I'm going to specifically ask you that as a test question, but you'll need to know that to do some problem solving. But yes, reactants on the left, products on the right, arrow pointing from reactants to the product. That's always the case in this course. I know I asked you on Monday, some of you have had real chemistry before, so as you know, it doesn't always work that way. Sometimes the arrows go back and forth, right? And then the reactant versus product just depends on which chemical reaction you're talking about. Is it going this way? Is it going that way? But anyway, yes, you definitely need to know reactants on the left, products on the right, right? Reactants what we start with, products the end material. And again, chemical reactions are just rearranging matter. We cannot create or destroy matter. We can only rearrange it. That's why I like to use this equation as an example. How many of you have ever poured hydrogen peroxide on a wound? What happened when you did? Or what did you witness? Not really how did it feel, but what did you see when you did that? Foamed up, right? Bubbled up. And here's the chemical reaction. This is why. So for every 2 molecules of hydrogen peroxide, once you pour it on a wound, it goes through a reaction, and the products are water and oxygen. And what happens when you mix water and gas? You get bubbles, right? So that's where the bubbles come from. By the way, that's just an example. I'm not going to ask you any questions about hydrogen peroxide. But you can see here, we have now completely different reactants and products. The reactants are hydrogen peroxide, which is deadly, by the way. You don't want to drink it. It's poison at the right dose. And again, so does pretty much anything. But anyway, it's not good stuff. So when it goes through the reaction, then we're just left with water and oxygen, right? Things we need for life. But again, we didn't create matter. We just rearranged it. So if you look here, how many oxygens do we have? 1, 2, 3, 4. All right, how many oxygens do we have at the end? 1, 2, 3, 4. How many hydrogens do we have to begin with? 1, 2, 3, 4. How many do we have at the end? 1, 2, 3, 4. So you see? We started and ended with the same amount of matter. We just rearrange it. It'd be like giving a kid or a bunch of different kids, like, all right, here's, 10 Lego blocks. Go build something, right? They all have the same matter, but then the products will all be probably something different because they'll do it in different ways. Same thing here. Any questions about this slide? All right. Next slide. At the end of this next slide, I'm going to have the next attendance word. So if you're online, be prepared to take a screenshot towards the end. And of course, you guys who are here in person, just do the regular thing. Anyway, let's talk about ionic bonds. There's different types of bonds. Seems like I'm missing a slide. I should have had a slide and told you there's three types of bonds that we're going to consider in this course. Ionic bonds, covalent bonds, and hydrogen bonds. We're going to talk about them separately. So here's the first one, ionic bonds. When an atom loses or gains electrons to fill its outer ring, so again, remember that's the purpose, to get a full outer ring, it becomes electrically charged. Because, as we know from our discussion on Monday, if something has more electrons than it has protons, it's negative. If something has more protons than it has electrons, it's positive, right? So it has a charge. Therefore, if something's giving up electrons or taking electrons, it's probably going to have a charge, right? If it's giving up electrons, it's losing something negative, so it's going to become positive. If it's taking on electrons, it's gaining something negative, so it's going to become negative. And that brings us to one word you definitely need to know, and I might actually ask you this definition, an ion. An ion is an electrically charged atom or molecule that was the result of gaining or losing electrons. That is what an ion is. We'll almost definitely ask you that. Slightly less chance that I might ask you about the two different types of ions. Cation and anion. Ions are positive because they lost electrons, right? So they're losing something negative, so they become positive. Anions are negative because they have gained electrons, right? And if you get more electrons and protons, then you're negative. All that makes sense? Just a lot of stuff to memorize. It's simple, just a lot of stuff to memorize. So that brings us finally to what we've been talking about this whole time, ionic bonds. Those are bonds between oppositely charged ions. So again, you've got these ions, whether they be molecules or atoms, they've been giving up electrons and taking electrons. So one of them's positive, one of them's negative, and just like a magnet, they attract each other. So that's what happens. That's what an ionic bond is. So the next word for attendance, I'm going to underline it, bonds. If you're online, you're going to take a screenshot of me pointing at it. So there you go. I'll sit here for a little bit so they have time to take a screenshot. Does anybody have any questions about ionic bonds? The next slide, I'm going to show you some pictures of what they look like. All right, no questions? We'll move forward. If you download the PowerPoint, you can watch this at a later. Wait, no, this is the picture first. Here's a picture. It's the very common ion. It's the first one we talked about in this chapter, actually, Monday. Anyway, when we first started chapter 2, I showed you a picture of fries with salt being poured on it. This is salt, right? Table salt. And it's called sodium chloride. So here's how this happens. Here we have a sodium atom. It has 1, 2, 3 rings. That outermost ring has 1 electron. Do you remember how many I said that the outermost ring is supposed to have? 8, good. So this one has 1, 2, 3, 4, 5, 6, 7. As some of you guys have already said, it needs 8. So this one has 1 on its outermost, but it needs 7 more. This one has 7, but needs 1 more. So it'd be a lot easier for this sodium atom to just get rid of that 1 on the outermost ring, and then that's no longer its outermost ring. It's gone, right? So now its outermost ring is the next one. So it now has 2, 4, 6, 8. It has 8 electrons on its outermost ring. It is now non-reactive. It's now positive, right? That's what that little plus means, because it gave up something negative. It gave up an electron, so it became positive. Chlorine, on the other hand, or chloride, once it gets it, takes that electron. And because it took the electron, it became negative, right? When you gain something negative, you become negative. When you give up something negative, you become positive. And again, just like a magnet, negative and positive things attract each other. It's a horrible, 2 horrible arrows or whatever. Any questions about that? All right, that's an ionic bond. If you download the PowerPoint, yes.
Why does that happen if it's supposed to have a, does it automatically happen? Does it switch back and forth?
No, there's definitely, the easy answer for our course is no, it doesn't switch back and forth. The more complicated answer, and I'm just brushing the surface, it's really chemistry is all about energy. So it's better for the energy for both of those things, for this one to give up an electron. Because like I said, it only has 1 on the outermost, but it needs 8. Once it gets rid of that 1, that is no longer the outermost. So now it has the 8 that it needs. It's stable. It has a nice energy. This thing gained its 1 electron, so now it has the full outer 8. So they're both at a great energy level. But again, the more complicated answer, if you were into real chemistry, some chemical reactions are reversible. It's all about the energy. But we don't even get into that. As far as we're concerned, that's not reversible. That's a great question. And again, just make sure you see the big picture here. These are not stable. This one has not enough electrons, well, depending on how you look at it. This one has too many electrons. Let's look at it that way. This one doesn't have enough. Now, these both have 8. Those are both stable. Good question. Any other questions? All right. And if you happen to send me attendance words today, it's Parks, right? Actually, you'll need to anyway because you came in late, right? So send the words. Remind me that you asked a question. I'll give you a little bit more extra credit points for that. I'll try to remember to do that with everybody, but if I don't, I apologize. Anyway, if you download the PowerPoint, everything I just told you, you can see a little animation. You can watch it in action. All right, let's talk about covalent bonds. So remember, there's 3 different types of bonds that we talked about in this class. Ionic was the first one. The next one is covalent bonds. What does it mean when someone says they're cohabitating? If you told your friends, oh, I'm cohabitating with my friend, what does that mean? Living with him, right? Yeah. What about the term co-parenting? If some divorced couples say they're co-parenting, what does that mean? Yeah, they're both doing the parenting. It's not like one's got the kid and the other one's don't, or the other one doesn't, so only one's doing the parenting, right? They're both doing the parenting. So you're already familiar with the prefix co, right? You're sharing parenting responsibilities. You're sharing a place to live. So covalent bonding is when atoms share electrons. They're not giving them up and taking them. It's not a bad divorce like the ionic bond was. This is a sharing of electrons. And again, if you can remember co, the prefix co, as far as we're concerned, is all about sharing. And I don't remember if I told you this or not yet, but that outermost ring I was talking about is called a valence ring. So hopefully those two things can help you remember that a covalent bond is when the atoms are sharing electrons. Technically, sharing one or more pairs of electrons. If I were to ask you the definition of a covalent bond, I wouldn't be so tricky as to change this part, the one or more pairs, right? If you can remember that covalent bonds are where they share electrons, and the other parts, doesn't matter. Here's another thing you definitely need to know later in the semester. This will be important. Covalent bonds are the strongest bonds that we talk about in this course. Of the 3 bonds that we talk about, covalent bonds are the strongest. That will be important later when I describe how DNA works. You'll see why later, towards the end of the semester. But yes, because that's going to be important later, I might test you on that. Yes, they also happen to be the most common bonds, but I'm not going to test you on that. Probably. Anyway, yes, covalent bonds are the strongest. Covalent bonds hold atoms together in a molecule. Put a question mark next to this. I'm not sure I'm going to ask you that. But yeah, technically, if they're together because of covalent bond, that's a molecule. But as far as I'm concerned, in this class, when we say molecule, we're just talking about any old atoms together. So that's why I put a question mark next to that. I'm almost definitely not going to ask you that. Once again, well, actually, before I put it on there, the next bullet point, what is the purpose? Why are they sharing those electrons? What are they trying to do? It's the same reason that they did in ionic bonds, the same reason they gave up electrons and took electrons. What are they trying to do? Stable. Become stable, good, exactly. And how are they becoming stable? What do they need to do to become stable? They're trying to fill their outermost ring. You definitely need to know that. If you send me the words today, remind me that you answered a question. And I'll give you a little bit more experience. Matter of fact, if any of you, if you send me the words today and you answered a question or asked a good question, just include that on there if you want. By the way, you asked a question about ions and I answered it, whatever it may be. Because I prefer us talking together instead of me talking at you, but it's 8 in the morning. It's hard to get people talking. Anyway, and it's also chemistry. People don't sit around talking about chemistry. Again, yes, they're trying to fill that outer electron shell. That valence shell is what they're trying to fill. Valence. That outermost is called the valence shell. Again, they are sharing electrons. They're not taking them. They're not giving them. They are sharing them. And there's 2 types. This is another thing you need to know, the 2 types of covalent bonds. So again, we're talking about covalent bonds, there's 2 subcategories. Sort of like the ions, not ionic bonds, but remember there's 2 different types of ions. Now I'm telling you there's 2 different types of covalent bonds. The 2 types are nonpolar, which is where the electrons are shared equally. Sort of like the co-parenting thing, right? Where I said they're sharing the parenting equally, right? Same here. Covalent, they're sharing the electrons equally. That's what, and I'm going to give you some examples. This will make a lot more sense when I give you some examples. And then, of course, the other one is polar, where the electrons are not shared equally. And again, I'll show you some pictures and explain this later, but for now, we'll leave it at that. Maybe one way to remember this is think about like our world is a polar world, right? We've got North Pole, South Pole, and everything in between. And if you think about it, it's really cold at the poles and really warm well, not really warm, but relatively warm everywhere else, right? The heat is not evenly distributed in our polar Earth. Does that make sense? So imagine if you can think about that, just think about it with electrons, all right? The electrons are not shared equally. They're going to one pole more than the other. Just like heat, coldness for our Earth. And of course, the opposite by definition then would be, if it's not polar, the electrons are just shared equally. And again, we'll come back to that. That'll be important later. I made myself a note. This is why I've got that little star. Let me see what that is. Oh yeah. Okay. Yeah, technically, if you were to read your textbook, it would say the two types of covalent bonds are non-polar covalent bonds and polar covalent bonds. I just shortened it because it's a PowerPoint. As far as we're concerned, we don't need to throw that in there because we're already talking about covalent bonds anyway. So any questions about that? All right, let me give you some examples of covalent bonds and why they happen and how they happen. And we'll talk about carbon. This will be a big one. You're going to use this a lot next week in lab. This is just an example. So everything I'm about to tell you, if you take notes, you don't need to write that down. This will not be a test question. But I'm going to show you how you can figure things out based on a little bit of information. So carbon. I wish I did this properly to where we could just look at one bullet point at a time. But here we go. Carbon's atomic number is 6. I would give you that on an exam, maybe, or in lab, and then ask you to figure something out based on that one piece of information. So, knowing that its atomic number is 6, I could ask you, how many protons does it have? We already talked about this in the last lecture. Its atomic number is the same as the proton, right? Atomic number equals protons. So if I say it has atomic number of 6, it has 6 protons. If I say it has an atomic number of 118, it has 118 protons. Make sense? That part's easy. The next part's pretty easy too. And then I'll say, all right, again, I'll just give you the atomic number, and then I could ask you all these questions. Its atomic number is 6. How many electrons does it have? All right, its atomic number is 6. Therefore, it has 6 protons. I didn't say anything about it being charged. It's not positive or negative, so therefore the protons number equals the electrons number. Therefore, it has 6 electrons. You guys with me so far? All right, it's pretty simple. Then, as I said, as far as we're concerned in this course, first ring holds 2 electrons. All the other rings hold 8 electrons. So carbon has 6 electrons. You can just draw it and see how many it has on the inside, how many it has on the outside. Or unless your brain works the way some people's brain works, you can just picture it and think, oh yeah, it's got 4 on the outside. But let me show you. If you were to draw it, that first ring, you would draw the 2 electrons. So 6 minus 2 is 4, all right? You still got 4 left. You draw the next ring, and you draw your 1, 2, 3, 4 electrons. Now we have all 6 accounted for. 1, 2, 3, 4, 5, 6 electrons. We've drawn a good carbon. And how many electrons does it have on its outer shell? It's right there in front of you. Count it and look at it, or just read that. It has 4. It has 4 electrons on the outer shell. But as we know, I've been beating this dead horse for a while. As far as we're concerned, everything needs a full outer ring, and other than the first ring, it holds 8. So if it has 4, then it needs 4 more. Does that make sense? Let me ask you this. If it was oxygen and it had 6 electrons on the outside, how many more would it need to be full? 2. Good basic math. Remind me you answer that question. If you can remember, get a little extra points. But yeah, so that's the point, right? They're just trying to fill the outer shell. This one needs 4 more, and therefore, as far as we're concerned in this class, however many electrons it needs to fill its outer shell, that's how many times it can bond. It does get a little bit more complicated than that in real chemistry, but for our course, that's perfect. It's simple, and it's that easy. However many electrons it needs is how many times it can bond. So in short, carbon can bond 4 times. And once again, I'm not going to ask you this as a question. I'm not going to say, I won't just give you a question where it says, how many electrons does carbon have on the outer shell? I won't do that. I might say, carbon's atomic number is 6. How many electrons does it have on its outer shell? Then you would go through this whole rigmarole. Okay, atomic number equals the protons. If it's not charged, then the proton number equals the electron number. You know, if it had, and then you can just figure out how many are on the inside, how many are on the outside. Any questions about that? Okay, next is an example of different ways to draw molecules. You do not need to know this. I'm not going to test you on this. I'm only bringing this up because I would hate for me to be talking to you about, I wouldn't talk about formaldehyde for any reason, but this is what we're looking at. I would hate for me to be talking about formaldehyde and show you a picture like this on the slide. And then, because it's so fascinating and interesting, you go talking to your buddies about formaldehyde, and you all look it up because it really is that exciting, right? And then your buddy pulls up a picture like that, and you're like, You're an idiot. That's not formaldehyde. I just saw the lecture today. Formaldehyde looks like that. No, it's not like that. The point is, there's different ways of drawing molecules. I'm not going to test you and ask you which one's the electron configuration or structural formula or space, blah, blah, blah. I'm not going to ask you that. I will point this out, though. The one you need to be familiar with, you're going to have practice doing this next week, is this one. Structural formula is what we will be drawing in lab next week. You're going to be drawing things like that. And we're going to go into this in more detail next week, but really quickly, since it's up here anyway, I might as well show you. Single bonds are represented by one line. There's a single bond, there's a single bond. Double bonds are represented by two lines. Triple bonds, even though you won't be drawing those in this course, are represented by 3 lines. Make sense? It's all pretty simple. So you're going to be drawing stuff like that. And remember, like I said, just as an example one more time, I said carbon bonds 4 times, right? Now it's only bonded to 3 other atoms, but how many bonds does it have? 1, 2, 3, 4. Because the double bond is 2 bonds, right? But well, that makes sense. Anyway, any questions about this slide? You don't have to know anything about formaldehyde. You don't have to know anything about the different types of models. You're just going to have to eventually draw some structural formulas, but not a formaldehyde. Actually, formaldehyde might be one of them, but it doesn't matter. Anyway, if there's no questions about this, let me show you this very quickly. If you download the PowerPoint, again, everything I just showed you, you can watch the little animation that shows how covalent bonds are formed. Now that we're done with that, let's go back to this idea of polar and nonpolar. Polar molecules, again, like we already said, that is the uneven sharing of electrons. I'm not going to ask you the definition of a polar molecule. But you need to know what a polar molecule is to be able to answer some other questions. Hope that makes sense too. There's a lot of things like you need to know the definition, not because I'm going to ask it, but because you need to understand the concept to be able to figure out something else. And this is one of them. Polar molecules have an uneven sharing of electrons, aka distribution of charge. Just like our polar Earth has an uneven sharing of temperature. One side of a polar molecule is slightly positive, not completely, and one side is slightly negative, not completely. If it was completely positive on one side and completely negative on the other, that would be an ionic bond. But it's not completely, it's just slightly. And the most important example of this, because we're going to talk about it a lot in this course, is water. Granted, I'm not going to ask you an example of polar molecule, but you do need to know water is polar, and let's explain why. Here we have 1 oxygen joined to 2 hydrogens. Let me ask you this. This is a good quiz to help you get ready for the lab and the exam. Hydrogen's atomic number is 1. So how many protons does hydrogen have? Good. By definition, it has 1. And it's not charged, so it's not a positive hydrogen or negative hydrogen. So how many electrons does it have? 1. Good. Actually, you know what? In this conversation, that's not even important. All right, there's hydrogen. Oxygen. Its atomic number, oops. Its atomic number, is 8. Do that. It's so hard to draw with this thing. Since its atomic number is 8, how many protons does it have? 8. Good. All right, so I'm going to try to draw this here too. It's red, so it's not going to show up, but that's 8 protons in that nucleus. These hydrogens have 1 proton apiece. And what charge are protons?
Positive.
Positive, good. So there's 8 positive things next to this oxygen. I'm not going to draw out all those 8 pluses. And there's only 1 positive thing next to those hydrogens. So if you're an electron, what do you attract? Actually, as an electron, what are you attracted to? Other electrons, protons, or neutrons? If you're an electron,
Protons.
protons, good, right? Because they're positive. Therefore, if you're an electron, you're trying to hang out with oxygen, right? Hydrogen's cool too. It's got a proton. You like protons, so you visit hydrogen a little bit, but you're more pulled towards oxygen because it has all those protons. Therefore, squiggle this out. Actually, now I'll just show you on the next page. Because of that, hydrogen or water is slightly negative on the oxygen end and slightly positive on the hydrogen end. Because again, those electrons are hanging out towards the oxygen because it has more protons. The electrons are just being where they want to be. Again, using the co-parenting idea, If there's parents that are divorced and they agreed, all right, we're gonna do this equally, 1 week with you, 1 week with me, so on and so forth, right? They try to split the parenting responsibilities. And then let's say like, I don't know, dad's a real prick, he's real mean, his house smells like cactus and cigarette smoke. There's nothing fun to do at his house. Meanwhile, mom's got a nice big house, smells good, she's nice, they eat good food, they've got all the technology that he likes to play with. So the kid's probably gonna wanna hang out with mom's house more, right? Yeah, sure, technically they're co-parenting, but let's be honest, the kid's gonna be trying to hang out with mom's house more. Same thing here, right? Yes, technically they're sharing electrons, but oxygen's got it going on as far as electrons are concerned. Anyway, all of this is important because this results in weak attractions between neighboring water molecules, and that is what a hydrogen bond is. And that is the third and final type of bond that we're going to talk about. You need to know all three. So we talked about ionic bonds, where they get electrons and they take electrons. We talked about covalent bonds, where they share electrons. And now we're talking about hydrogen bonds, which in a way, and I've never seen it written like this, but I think this is a great way to describe it. It's almost like a weak ionic bond. You're still dealing with two things that have charges, right? It's just that the ionic bond are fully positive and fully negative. Here, it's like, slightly positive, slightly negative. And again, this will be important later. Just like I said on the previous slides, covalent bonds are the strongest bonds. That will be important later. Likewise, hydrogen bonds are the weakest of the bonds, and that will be important later, but not for this exam. Any questions so far about hydrogen bonds? The next picture I'm going to show you will make more sense, I think. All right, so there we go. You can see all these water molecules interacting with each other. You can see these slightly positive hydrogens are attracted to that slightly negative oxygen. This slightly negative oxygen is attracted to this slightly positive hydrogen. This slightly positive hydrogen is attracted to that slightly negative oxygen. There will be 2 test questions on the exam. People will screw them up. It's not hard, but they're easy to get confused. So I'm going to go ahead and tell you about it now so you don't get them confused. One question asks, what kind of bond holds together a water molecule? So what kind of bond is holding this one molecule together? It's covalent bonds. These hydrogens are covalently bonded to that oxygen. Then there's going to be another question that says, what kind of bond holds adjacent water molecules together? Not one water molecule, but adjacent water molecules, and the answer is hydrogen bonds. I don't mean for it to be tricky. It's just that because they both ask about water, it's a little bit tricky. So don't get fooled on the exam. Any questions about that? All right, we're moving along quite nicely. That's it for the bonds. So let's talk about elements and compounds. Next, at the end of this slide, I'm going to give you one more independent work. One more attendance work. So if you're online, get ready for your screenshotting. Anyway, here we go. Elements and compounds. This is not from your textbook, so I'm really not going to ask you any questions on it. I'm just going to talk about it very quickly. There are 92 naturally occurring elements. If you look at the periodic table of elements, you can see there's more than 92, but the other ones are not naturally occurring. You can look that up for independent work if you want. We don't get into it. Some examples include carbon, oxygen, potassium, gold, 88 others. You don't need to know that there's 92. You don't need to know those examples. You're going to be very familiar with carbon and oxygen by the end of lab next week, but we'll talk about that later. Each symbol is derived from an English, Latin, or German name. That's yet another thing you don't need to know for the exam or this course. But in case you're wondering where they got the weird symbols, that's where they got them. Like lead symbol is Pb. Now, that's nothing like lead, right? But that's because it's based off of its Latin name. Here's something you do need to know, even though it's not in the textbook. And I typically don't do this, so I'm making a big deal. Oh, whoops, sorry. Attendance word. Sorry. The next word for attendance is cat. So if you're online, you take a screenshot, me pointing at this indoor cat, and that's where cats belong inside. Another independent word topic if you want to look that up. Cats are very invasive, destructive. They belong inside. Die on that hill. Anyway, no question about that. Let's move forward. This part you do need to know. So if you're taking notes, even if you don't write it down, just say, hey, remember to study the PowerPoint slide with the Bill Nye meme on it. There are 25 elements that are essential to humans. So So you don't need to know that part. What you need to know is what I call the big four. After lab next week, I have a feeling you won't need to study that because you're going to know the big four because you've been drawing them and drawing them and drawing them. But the big four are oxygen, carbon, hydrogen, nitrogen. You need to know those. You don't even need to know that it makes up about 96% of the body weight. That might be an extra credit question or something, but I'm not going to ask you the number. Just know that it's the big four for a reason. Like a large majority of what makes you up is oxygen, carbon, hydrogen, and nitrogen. It's easy to remember oxygen and hydrogen, right? Because we all know you need life to live. You need water to live, and water is made up of oxygen and hydrogen, so that makes it that easy to remember. We all know that you breathe in oxygen, so again, easy to remember. We all know that you breathe out carbon dioxide, which is carbon and oxygen. So that, in my opinion, oxygen, carbon, and hydrogen should be easy to remember. Nitrogen will be a little bit trickier, but again, you'll have plenty of experience with this on next week in lab. So again, that's the big four. You need to know those. Let's move through these other ones really quickly because I probably won't ask you any questions about this. But the other ones, right? So again, about 96% is the big four. What about the other 4%? Well, there's 7 elements that make up most of the other 4%. You don't need to know about them, but they're great independent work topics I'm going to talk about. I'm going to talk about some of them. They're just examples, so don't study any of this because I'm not going to ask you about them. The calcium is one of the 7. It's important for bones and teeth. It's found in dairy products, sardines, green leaf vegetables, whatever. So look that up for independent work if you want. What happens if you have not enough calcium? What happens if you have too much calcium? Because remember I told you, essentially everything's a poison. It's all about the dose.
I have weak bones. And
Yeah.
you can have fractures.
Yep. Oh, speaking of which, this is a great, I'm so glad you answered that. He knows that. I think most people know that. But even though we know that, if you were to look that up for an independent work topic, it doesn't matter that we all know it, find a source that says that. So it's a fact, so you have to back it up with a source. Even if some common fact like that. So I'm so glad you said that. Same thing with phosphorus. Look that up if you want for independent work. What happens if you have too much? What happens if you don't have enough? Your body obviously uses it for DNA, but what else is it used for? It's found in eggs, beans, and nuts. Where else can you find it? Moving forward. Actually, that's it. Of the 7 that make up the majority of the other 4, those are the only the 4%. Those are the only 2 we talked about. Not because they're more important than the other 5. Those just happen to be the random examples. That brings us to the next thing. This is sort of important. There's also 14 trace elements. I'm not going to ask you how many there are. I'm not going to ask you any questions about them. Just in the back of your mind, just know that trace elements make up a very small portion of your body. They're essential, but they're very essential in very small amounts, which is really good for the independent work topics I was talking about earlier. Because they're needed in such small amounts, you can imagine that these really could be bad for you if you had large amounts. So once again, iodine for independent work if you want it. How much is too much? How much is not enough? What happens if you have too much? What happens if you don't have enough? Other than the stuff already listed, right? If you have a deficiency, you get goiter and enlarged thyroid. I'm not going to ask you that. This is some places you can find it. Iodized salt, that's what they mean by iodized salt. They've added iodine to your salt because people weren't getting enough iodine in their diets. It's another independent work topic. You can look at it. It's slightly interesting. It's interesting as salt can be. You could read about how that came to be where they started putting iodine in salt. Fluorine's another good example. I love this one because there's a lot of conspiracy theorists out here because and this is how they thrive, they can correctly say that fluorine is a poison, just like everything else I talked about. Because if you have too much of it, it's poisonous, just like every other thing that we're talking about of these trace elements that you have to survive. You need fluorine to survive, but if you have too much, it's bad for you. So once again, same stuff to look up for independent work. How much is too much? How much is not enough? What happens if you have too much? What happens if you don't have enough? Where can you find it? So on and so forth. But again, these are just examples. I'm not going to ask you any questions about fluorine or iodine or any of the other 12 trace elements that you can look up for independent work and ask the same questions. How much is too much? How much is not enough? What happens if you have too much? What happens if you don't have enough? Where can you find it? How does your body use it? So on and so forth. Any questions about that? Okay. Really quickly, I like this too. So speaking food, like I said, we add iodine to salt, right? Salt doesn't have iodine in it normally. We just put it in there because we need it. Same thing here. When cereals say they're fortified, they mean it's fortified. There's iron. They put metal in your cereal because you need it. You need iron. And what I love about this example is maybe I can share them on Facebook. There's at least 2 different videos on the internet about this. They both do the same thing. Guy or a person takes cereal, puts it in a blender with water, blends it up to it's just a big squishy mess for both of them. And then they put a magnet next to the blender, and sure enough, the metal that's in the cereal is attracted to the magnet. It's the same thing both people are doing, but one person's doing it trying to scare you. Listen, I don't know what these people are trying to do, but they're trying to poison you. They're putting metals in your food. I can prove it. And they shows it. Oh my God. He does it in a scary way. Or she, I don't even remember. Then the other person's like, we enrich our foods. You need iron. This is proof that they do it, right? So they're doing the same thing. One's trying to scare you, one's not. Which is such a great example because this is what people do. People are trying to scare you by giving you the truth in a scary manner. Anyway, this is a good thing to take 50. It's a good place to end. Just know this. You don't need to study this. You don't need to know these percentages. Just know what the big 4 are, and that's that. We will see you 10 o'clock today. Don't be late. Late, you can't come in, and means you'll get a 0. So be here at lab at 10. That's it. No last word for attendance. And there's only one person that hasn't turned in a pre-lab. Hopefully you know who you are. Contact me between now and 10. We can figure something out. Because I don't want you to get 0 on your first lab. And if you came in late, make sure you text me. Email me.